for the conference and for the opportunity to speak. I will speak about my work with Pedro Vieira, and the talk is divided into two parts. One is given by me and another one by Pedro. So this work is about relating finite size corrections to the Bethe equations and quasi-classical corrections from the string side. So I will basically speak only about corrections from finite size corrections in Bethe ansatze. So this is plan of my talk. So it will be short introduction, then I will explain how to use Baxter polynomials to efficiently compute finite size corrections in the SR2 Bethe ansatze, and then to generalize to the nested case. Then I will show how roughly the integral equation can be derived, which describes the finite size corrections. And finally, I will mention how this approach can be applied to the Bethe equations. And then Pedro will start speaking. So as an introduction, I have only one slide. So as you know, the right lists two scalar fields and an equal for superior theory, which one can denote by arrows. And then this kind of local long operator can be mapped into the spin chain state. And then the mixing matrix turns out to be an integrable spin chain, Hamiltonian, as it was shown by München and Zareb. But in fact, the first part of my talk, I will use mainly SL2 sector by some reasons, because this subsector can be diagonalized by means of this Bethe ansatze equation, and this Bethe ansatze equation has a nice feature that all solutions are real numbers. So the set of beta roots is always real for this kind of equations. That is nice to visualize. And moreover, SU2 sector was already described in details during the talk of Nikolay. So I will focus on some particular scalar limit, namely to the limit when number of magnons is of order of the length of the spin chain, and also I will assume that root scales like the length of the spin chain, and in this limit beta roots condense into cuts. So I have this animation. So this is density of the roots, and this is u over spin length, and you see the roots are condensing into three supports when I increase proportionally S and L from 0 to 200 magnons. So this is just to visualize this numerics. You see that beta roots are condensed into some square roots, and density you see is obviously some square root function close to the edges. So finally we will have some Riemann surface with square root singularities which are cuts relating to different sheets. And as Nicholas already said, these types of configuration can be related to the classical solutions, in this case of some Landau-Lifshitz model. And in the case of the Bethe equations, by construction they reproduce classical spectral curve of the string in the background of ADS5 cross S5. So We are interested in the finite size corrections, which one can think about as being a quantum correction to the classical solutions corresponding to this cut condensate. And so we want to expand Bethe ansatze equations in this limit. And here some funny things happen, that when we expand the sum for large L, first term is obvious, is just rho is density of Bethe roots. We expand log and we get this denominator, the singular kernel. And this term is somehow cannot be seen instantly from this expression to the left hand side, and it is called anomaly by this reason. So here I introduce P, which is a standard resolvent minus some simple function. So finally, Bethe ansatze equation after this expansion can be written as this compact form. It just average on the cut of this P is equal to 2 pi n minus this anomaly term. So let's see how to derive this anomaly in this simple case of SL2 spin chain. So for this, let's consider the Baxter polynomial. So the condition that this function doesn't have poles at u equal uj is equivalent to, in fact, to the Bethe ansatze equations. And I also divided by some function, so it is not really a polynomial, as indicated by this sign. So, at the next step, let's consider this equation. So, what can we see? Can we say about exponential of IQ? Is that it is a solution to some quadratic equation with analytical coefficients, and this implies automatically that this equation defines some algebraic curve with two sheets, so which can be written in this form. So for and note that this equation is right to all orders in it. So even for a couple of roots, we can define in this way some algebraic curve, and always it will satisfy this condition that Q can jump only by 2 pi n, because exponent of IQ is a well-defined single-valued function on this two-sheet Riemann surface. But our goal is to expand at large L, and so let's expand this T function, and we get this simple expression to the leading and subleading order, and then we solve this equation, and we get that Q is equal to pi plus this term. So when we substitute here, we immediately get this equation. So it was for SL2 case, it was well known, of course, before, and I showed it just to develop the most efficient technique to compute this anomaly term. And now I want to apply it to a more complicated case of the nested Bethe ansatze of SU3 Bethe ansatze. Now you see there are two types of roots, U1 and U2, and there is self-interaction and interaction between them. So it is more complicated system apparently. And now we can, as Volodya explained it, already introduce a set of Baxter polynomials. So namely, we are interested in these three Baxter polynomials, and again, from Bethe ansatze equation, it immediately follows that these three functions they have no poles far enough from the origin. The only poles are produced from these denominators, and they are trivial poles. So now to repeat the trick above, let's write the following equation. Now it is of the third order equation in the exponent, and all coefficients are again analytical functions everywhere except some vicinity of 0, and this automatically implies that this equation defines some three-sheet Riemann surface, which again we can write in this way, where slash it's average on the cut. So it just implies that when we pass from one sheet to another, Q through the cut, Q can jump by only by 2 pi n, because exponent should be continuous function when we.
What is dictating that you're actually thinking that it's branch counts? I mean, given this three-sheet of color, you could have monodromy 1, 2, 3, you could have 3 sheets come together.
Because I think it's equivalent to some three-particle scattering, which is suppressed usually. I mean, it's highly non-probable that 3 sheets.
So I agree that there's some sort of generic assumption, but it is actually implicit, is it, in your T? I mean, there's nothing about your T's that are preventing it.
Yeah, probably there is nothing, but I'm considering the the generic situation. So this degenerate cases, they probably don't realize the solutions will be on this equation, I guess. So again, we have this equation, and we can expand the T's and solve in favor of Q's, and what we get is the following. So you see now more catenges appears in the nested situation. So before we had only one catenge, but now there are lots of them. So let me remind what is the catenge. It is also here. And P's are some combinations of resolvents again. So as I already said, set of Q's should define some Riemann surface. And let's concentrate on this cut, which connects neighbor sheets. So we subtract this from this and slash on the cut, and what we get is from it is 2 pi n, as we know, because it is a perfect Riemann surface, and Q's are well-defined functions up to 2 pi n on the surface. And so finally we get this extra catenge coming from this. And if we repeat the same procedure for this bigger cut, something more complicated appears, namely this combination of 3 catenges. So this one can think as being a usual anomaly. This is some generalization for the nested case. And let's understand why equations look so differently for different cuts, the simple ones and complicated. For this goal, let's consider discontinuity of Q2 on the place where there is a branch cut on Q1. Of course, Q2 is continuous function here, so discontinuity of Q2 is 0, but nevertheless it is not obvious that discontinuity of the right hand side is 0, and what we get is some condition on discontinuity of P2, which gives us difference of the densities of the roots of the type 1 and type 2. So let me show you on the picture. So in discrete situation, this curve corresponds to this solution of the Bethe ansatze equation, and the roots of the different types, they form these bound states, but U's are not exactly equal but slightly displaced, and this give rise to the mismatch in the density. And now we know exactly how to calculate it. And we can immediately write equation for the density of the roots of the type U2. And this term comes exactly from this mismatch. So this is the result for SL SU3 case. Now we are ready to deal with the most complicated thing we have, this Bethe-Schneider equations. So it looks scary on first sign, but we see that in fact these two parts are exactly the same, and we know how to deal with them. And we again can compute mismatch in densities and derive this equation. So here the H's are projections of the resolvents of the type 4 on the cuts, and these terms are coming are coming from the mismatch of the densities. So these are my conclusions, that it is possible to derive some integral equation for the quantum corrections to the configurations of roots, to the classical configurations of roots, and on the next talk it will be matched with a quasi-classical string quantization. So 4 minutes. So this I don't want. So it's also helpful to derive for the derivation of the above equation. It was important to have dualities, namely these two different solutions of Bethe ansatze equation. In fact, they have exactly the same charges, energy, and all local charges are the same for these two solutions. And the symmetry can be explained by this equation, and there is duality given by this equation, which maps these types of solution to this types of solution. And using the solutions, you see this bosonic duality just exchanges sheets in the continuous limit. We can reduce cut of arbitrary complexity by consecutive application of this duality to a very simple cut, which is easy to deal with. So that's all.
In deriving the finite size anomaly, you start from the Baxter formulation of the Bethe and one-loop Bethe ansatze equations.
Yes.
Do you know what the Baxter formulation of the Bethe ansatze equations is?
No, I don't know, but
So you must have used a different method.
yeah, in fact I did, but I just wanted to cheat in this situation. And in fact, you see these parts are exactly the same as for SL2.
Oh, I see. You're using
So in fact, even without Baxter equation, just knowing how to compute mismatch for a given set of equations, if you forget about Baxter, you know how to compute mismatch of densities, you can immediately compute for this equation the mismatch.
But not for the whole set.
And combining this together with this dualities, it's enough we get enough information to compute everything.